As you all know, prior to the first page, the first real page of Laws of Form, Spencer Brown inserts Chinese characters from the Tao Te Ching, which Heinz von Foster has given the translation, "The beginning of heaven and earth has no name." We could think of that as saying, before there are distinctions, there are no names. And he goes on to say, one immediately starts turning logical somersaults when one asks about the beginning of the beginning. The question of the beginning is one of the fundamentally unanswerable questions, undecidable questions. However, in the paper that I'm presenting, which is about the mathematics of the B4 calculus, which is a four-valued cyclic extension to laws of form, in this paper, the approach falls within the tradition that says there are precedents to distinction. You can see it here. In the BF calculus, we invent or we imagine a new symbol, the imaginary mark, which I'm drawing as a mark with an I on it. So whenever the I is there, it's the imaginary mark. And the imaginary mark is related to the mark of distinction, to Spencer Brown's mark, in that two nested imaginary marks are equivalent to the regular mark. And because two nested regular marks are equal to the unmarked state, it therefore follows that four nests of the imaginary mark are equivalent to the unmarked state. So the imaginary mark cancels in a cycle of four. The motivation behind the paper and behind starting this project quite a few years ago was, first off, to see if it were possible to develop a calculus based on this cycle 4 cancellation, which in mathematics is known as arithmetic modulo 4, and also to further develop the concept of imaginary logical values as Spencer Brown first developed them and as people such as Francisco Varela and Liu further developed. And the key idea that was looking to include was the idea of the imaginary mark should not just be a value, but it should also be an operator operating on other values. So the imaginary value operating on something called x, a single nest, we can see as a rotation of one turn. A double nest does a rotation of 2 turns, a triple nest does a rotation of 3 turns, and then a nest in 4 imaginary marks is the same as not turning at all. And this means that the imaginary mark acts exactly like a clock that is marked with only 4 quarter hours. And the idea of modular arithmetic is familiar to almost everyone, at least everyone who's ever interacted with a radial clock, that is. Although that pattern is well known, people don't necessarily know that they know modular arithmetic until they happen into an abstract algebra course or something in which they say, oh, we're doing modular arithmetic. And one sees other familiar examples in everyday life with order 4 cancellations, such as the seasons and the calendar, and in traffic circles, which are getting built more and more these days. They went away and they've come back. I've personally seen a driver in Boston miss their turn and decide they needed to back up around the rotary, and they clearly didn't have the concept, even the pattern of modular arithmetic in their head. There is I call pure pure containment, which is in the title of my talk, when ordered pairs are not used. But there's an equivalent notation that was due to some work that Lou did quite a long time ago in the 1980s that uses ordered pairs. And in that notation, the ordered pair AB, the imaginary mark, turns that to a swap of A and B with only the B negated. And one finds that also has a cancellation of order 4, and it's an isomorphic approach to what I'm mostly talking in the paper. I'm also going to weave in a bit of that notation toward the end. Can one form a calculus? That was an easy question to answer. As long as one, working with the cancellation order 4, as long as one defines the rules for juxtaposing the imaginary marks in the correct way, then there is a calculus that satisfies the initials and consequences of the primary algebra. And the key thing is to make it the case that one imaginary mark, and I'm using a shorthand notation, just that's 3 imaginary marks that are nested. And if those two are juxtaposed together, they have to be equal to the mark, which, do remember that the mark is a double nested mark. And using the sets of juxtaposition and the cancellation in the arithmetic for the BF calculus, then calculations are possible, and this is just one simple example of an expression in this in the BF arithmetic. We see 2 instances of single marks next to each other, and rule 4 says that they can be collapsed into one. This is simply the law of Collings for identical versions of imaginary marks. And then applying rule 3, which was the one in the blue box, that translates into changing 3 and 1 into 2 nested marks. And the same rule gets applied, and this expression cancels to the marked value, or to the doubly marked value, the doubly imaginary mark. And this is just an example, but as it happens, it's provable that every expression in this arithmetic will simplify to one of the 4 simple expressions, and those 4 simple expressions are single, double, triple, and quadruply nested imaginary marks, the last of which is equivalent to the unmarked state. And it is also provable that each of the Spencer-Brown's 2 initial equations, position and transposition, hold for all 4 values, all 4 simple values, and so does the consequence generation. In fact, the entire Spencer-Brown algebra is satisfied by this. You would have to plug in a lot of values and do calculations to satisfy yourself on this, which we're not going to do. However, the BF calculus is not axiomatically complete simply based on Spencer-Brown's 2 initials. I'm going to take you through a quick tour of what is very interesting about the BF calculus, and just hit on the highlights. We've kind of laid down the foundations. The very first important point is the introduction of a new initial equation. And this is a variation that I call split generation, which is which starts with Spencer-Brown's form of generation, A mark B, A B mark B. And we apply the fact that the double imaginary mark is equivalent to the regular mark, same formula. And the act of splitting the mark of distinction is the key thing in split generation. We'll insert C, which stands for any possible expression in the BF calculus, and takes tremendous, by the way, energy, psychic energy, to split the mark of distinction. As you can see, that fellow there is he's pulling a distinction apart. And it is again possible to show that the form of split generation is valid for the calculus. And based on that split generation and using what's been referred to a couple of times today as the Bricken initials, with the first two Bricken initials plus the split form of generation, there is an axiomatically complete set of initials for the BF calculus, and this is a new result. A second aspect of the tour of the calculus is there are some new consequences that I developed in the process of working on these. The first is I call extraction, and this form, it's relatively easy to prove that is not derivable from Spencer-Brown's initials, so that's why it's important. We won't work through the whole demonstration, but there's a demonstration using the three initials, and it's a complicated demonstration that involves a lot of interplay, which it's for anyone who wants to get into this calculus, that's important to understand how things work. Another consequence I call disintegration, and disintegration is an important consequence in proving the axiomatic completeness of this calculus. And why it's important is it takes an expression with two juxtaposed items under the imaginary mark, and it separates out all the imaginaries so that A and B are never part of the same imaginary. They are under a double mark, but not under an odd imaginary. And that is a key step in doing the proof, the completeness proof. And basically what it allows us is to use the same grouping principles that Spencer-Brown used to prove that all expressions in the primary algebra have a normal form. We'll get to that in a second. There are also two new distribution laws that I call left and right distribution. And in fact, this calculus has a total of 12 distribution laws that are satisfied, but these two are the particularly interesting ones. And they play a role in the possible interpretations of this calculus. I mentioned a normal form. I prove that every expression that has a variable in this calculus, a variable x, takes the form that we show here. And basically they're all combinations of odd and evenly marked x's, and then a1, a2, a3, and a4 are either constants if x is the only value, or if there are other variables besides x, then they're contained in a1, a2, a3, and a4. And the idea behind the importance of the indicational normal form is that provides the tools for doing an induction proof to prove the next result. Just in comparison in laws of form, there are kind of two variants on the normal form, one that Spencer-Brown uses in the book, and one that is also implicit, and that compares to what I just showed you. the number of unique expressions in laws of form that has one variable. There are exactly 4 such expressions of one variable, and 16 unique expressions of 2 variables in a 2-valued system. In comparison, in the BF calculus, there are 256 unique unary expressions, expressions with one variables, and there's like 4.5 billion expressions that have 2 variables, and you get ridiculously large with more variables than that. And then the BF calculus is axiomatically complete. Just like laws of form is axiomatically complete, the BF calculus, if it's provable that f equals g, then it's also demonstrable from the set B1, B2, B3 that we talked about before with the Bricken initials with split generation. Now, interpreting the BF calculus is challenging because of how many possible interpretations that there are. Oops. I like the parable of the elephant and the blind man to talk about this. The idea is the blind man who's holding an elephant's trunk thinks he's got a hose in his hand. The one that has the tusk thinks he's handling a dagger. The one with the legs a tree trunk, and the one with the tail thinks he has a rope, or she has a rope. And the situation in dealing with mathematical logical systems is not dissimilar that one starts from a set of hard initials and says that's the system when there may be a common underlying system. Some possible interpretations of this calculus, I'm not going to explain them all, but the post-algebra of order 4 was the first multi-valuable, one of the first multi-valued systems ever made by Emil Post in 1920. Boolean algebra of order 4, various modal logics, the finite field F4, and the wave, and Lou Kauffman and Francisco Varela's waveform algebra, as well as Belknap's system 4, or logic 4. I'm just going to briefly talk about the 2 of those to explain. Belknap's 4, the 4, and in this we'll use ordered pairs. Belknap's 4, the idea is, that there is a definition of an OR operation that works on a lattice going this way, and the lowest element happens to be the one that's marked, unmarked, the highest unmarked, marked, and then there are 2 intermediary values at the top and bottom. The expressions in this logic for those happen to be these, which appeared in the equations, the left and right distribution equations I showed you before. In the waveform algebra, the way that OR and are defined is up and down in the same structure, and this is much more familiar to most people because and OR are simply on a pairwise basis, they're just what and OR would be if you applied them to the left and right sides, and the equations for those are the same as normally so for the primary algebra. There are very different definitions of these logics. Belknap interprets his system neither true nor false, false and not true, true and not false, and finally both true and false. And Belknap's intention was to deal with situations where there's contradictory information coming in. An AI system where the car says you're going to crash and you're not going to crash at the same time, for example. In contrast, the waveform algebra's purpose was to well, it was about incorporating waveforms and systems that feed back and oscillations, and the two extra values in their system were defined as as starting with marked or starting with unmarked phases of oscillations, and
both cross to equal themselves.
Right, exactly. The negation in the logic 4, using this, we'll just show the results here. That's the equation in the BF calculus. This is what it looks like in paired notation. It's simply shifting A and B. You can do this with the little card I've given you, by the way. Probably out of time, right? The way you do it is start with the box. One side of this has a black mark around the edge and one doesn't. That's the front. Start with the unmarked side on the lower right. And simply, let's see, I have to turn it toward me. To do the Belknap operation, do a diagonal turn like this. And what you'll notice is that swaps the red and blue singletons and leaves the double and the non-marked invariant. So that's Belknap's negation operation. And then the waveform negation, what it does is that it also swaps, but it swaps and negates. And take your card in this case, again from the same starting position, and this time do a diagonal flip in the opposite direction. There's only 2 diagonal flips possible, and that one swaps the unmarked and the doubly marked and leaves the blue and red singletons the same. If you do one version of the side-to-side swap here, by the way, you'll end up with Lew's interpretation of Spencer Brown's handling of the map theorem, coloring maps. Whoops. Combining the two logics, if you combine the two, my graphic had them exploding into each other, but if you add the two together, or if you simply add the one negation operation that was missing from the other, you complete the logic, and it becomes equivalent to the BF calculus. I've been told I have to stop, which is good. We have 2 articles, one with Lew that's posted on the archive, and a copy of the article that I would be presenting here. Did I eat up my question, Mike? Are there questions? Lew?
Well, I'll just add the obvious comment that you didn't quite get to, but the square root of -1 was defined by Hamilton, William Rowan Hamilton, by by changing an ordered pair from AB to -B, A. So that operation in ordered pairs goes all the way back to Hamilton's way of thinking about complex numbers. So this is a way of bringing complex numbers directly into your B4 is a way of bringing complex numbers directly into the form.
I wholeheartedly agree with what Lew said. That is expressible in matrix form, and I would add to that well, never mind. Somewhere it is. Yes, I would add to that there's also an extension of this to 16 values with the quaternions that builds on this.
And now I have a terrible question. You know that people like Shea Zellweger have written the 16 connectives in ordinary Boolean logic in the form of a logical garnet?
Yes.
Right? And it looks like a projection from 4 space, and it's a beautiful polyhedron. So we have to ask the same question about the billion.
The 4.5 billion. Why don't you assign that to one of your grad students?
So how many would it be with quaternions?
Pardon?
It's a billion with your ordinary complex numbers. How many with quaternions?
For 2 variables, it would be 16 to the 16th power to the second power.
It'd be absolutely enormous.
Right.
Luke, I'm sorry. I'm just, this clearly is a modernized version of what you did in your paper of imaginary values and logic, right? In which you
An extended kind of version with new things in it.
Yeah.
Yes, I mean, he isn't just modernizing.
Yeah, I realize it's a whole.
All of the consequences and so on came at looking at this process with just the single operators. I only worked backward on this once actually talking to Lou about it.
Okay.
And all of the consequences and so on apply to both.
That's
equally.
very interesting.
And the interplay between the two, if this turned out to be important to use for some reason, I would want to be working in both sides of this.
We still have time for a question or two.
I'll show you the other area where we're extending to if no one has questions, which there is an application to and specifically with the card I gave you to expressions with using braids, mathematical braid groups. And one of the most excited times that I've seen Lou get was when we first were working on the braid idea. So I'm not sure we haven't fully developed it, but the braiding permits this to be extended from just a pair to any n sets, an n tuple. We're pretty sure.
Round 4.